So there will be two types of problem that will come across: regression and classification. In regression, we have y, our dependent variable, which is quantitative, and we regress it onto our independent variable x. Let's say cost of production or sales, etc. While in classification, our dependent variable y is qualitative, and our aim is to classify this qualitative variable based on the independent variable x. So let's say we have colors, shape, size of cherry as our independent variables. So here we will try to classify a given fruit as cherry or not a cherry based on these independent variables. Now there are different algorithms that we will use to model these problems. However, there are methods that can be applied to both the problems. Also, all the methods that we will learn in our course can be applied irrespective of the type of the predictor. That means, irrespective whether the independent variable is qualitative or quantitative, all the methods that we are going to learn can be implemented. Now there is an important concept called bias-variance trade-off. First, let's understand what these two terms are. So first we will see what is bias. Bias is the error introduced by approximating a real-life problem using a simpler model. So as we saw earlier, we assumed a linear relationship and built our model, while in reality, the relationship may or may not be linear. So due to this assumption, there will be some error that will constitute to bias. Now let's say we build a model and it performed very well when we tested it based on our sample data. But then when we gave a new data, then the performance of the model dropped. This is called variance. Ideally, our model should be generic. Change in data should result in small variance. That is the whole point of modeling. We take past information and then predict the future. But if our model is not consistent, then the whole purpose is defeated. But the issue here is that we cannot reduce bias and variance together. Because if we reduce one, the other will increase. That is why we will have to do bias-variance trade-off. So this is a complex and an important aspect of model building. So here in the below table, it shows what happens if we choose a simpler model such as linear model, which is easy to understand, explain and work, vis-a-vis if we choose a non-linear shape. Now this is a very important table and I've compiled it such that it gives you a host of information in one place. So do keep it with you. You can refer to it in future as well. Now if you see the table, if we choose a non-linear model, which means our estimate fx resembles the actual fx, then flexibility of the model increases. The shape becomes more flexible. As a result, bias reduces, but variance increases. Hence, our prediction power becomes better because we have approximated our function to the actual function. However, our inference and interpretability of the results decreases because our model becomes more complex, and hence it can lead to overfitting. Now on the other hand, if we choose a linear model, which is a simpler model, then the flexibility decreases. As a result, bias increases, which means there will be more mismatch between our estimated function, that is f dash x, and the actual function, that is fx. Now the bias is increasing, hence variance will decrease. As a result, the prediction accuracy will also reduce, but it will increase the inference or interpretability of the results. Now this approach can lead to underfitting. So bias variance trade-off is basically finding the common grounds so that we neither underfit our model or overfit our model. Now it is easier said than done, but nothing to be afraid of. Just saying that it comes with a lot of experience and you will be doing it throughout your career. But I hope you have got a fairly good understanding of bias variance trade-off.